Okay, so today we're going to talk tornadoes. Now, it's worth pointing out here at the beginning that tornadoes can form in all kinds of storms. Even a single-cell storm with the right conditions could end up producing a tornado. But that said, most of the violent tornadoes, the tornadoes that cause significant damage, those are mainly going to be associated with supercell storms for the most part. And so that's what I'm going to focus on here mainly, is tornadoes associated with supercells. So let's first go through and review the structure of a supercell. We looked at this quickly in the last screencast, but let's review it here again. So first of all, to set the context, this storm, illustrated in this schematic, is forming an environment in which the winds at upper levels are blowing in the direction of this arrow, which listed in the figure is to the northeast. So the winds are blowing towards the northeast, or they're southwesterly winds, if you like, at upper levels. And to a first approximation, at least, the storm tends to move in the direction of the mid to upper level winds. And so this whole system is moving off in that same direction towards the northeast. It actually veers a little bit to the right of the wind, but to a first approximation, it more or less follows the wind. So what are the important features of this guy? Well, we've got our warm air over here. Actually, I should point out, if this thing is all moving towards the northeast, then our perspective must be from the southeast. That is, we're viewing this system from the southeast of the storm. And so that's the direction of the warm air also, is down here to the southeast of the storm. And so that's feeding into the storm here. And then it goes through and, up into the updraft of the system. And the distinguishing characteristic of supercells actually is that they have this rotating updraft. So as the air comes into the updraft, it goes through this rotating updraft. And a supercell will typically have at least one downdraft. But a lot of the stronger storms, most of the storms that produce tornadoes, are actually going to split into two downdrafts. You've got one downdraft over here on the front side of the system, i.e. on the side of the storm in the direction that the system is moving, the front side. And that's called the front flank downdraft, because it's on the front side. And then you've got a second downdraft over here on the back side of the system, called the rear flank downdraft. Each of these downdrafts will build up a cold pool below it, and that cold pool will spread along the ground, which means that they're also each going to have their own gust front. So just following the naming convention of the downdrafts, we've got our front flank gust front associated with the front flank downdraft, and then we've got our rear flank gust front here on the back side of the system. And then the last thing I'll point out, I guess I'll point out that the updraft happens to be typically configured in such a way that it sits right where these two gust fronts come together. These two spreading gust fronts along the ground kind of actually sort of funnel the warm air into the updraft in a way. And then the last thing I'll point out is that typically at upper levels, you have this structure where the cloud sort of overhangs in the direction of the winds. Basically what's going on is that the cloud ends up getting pushed downstream by the winds, and so you get this feature that sort of extends in the direction downstream. It's often more exaggerated than they're showing in the figure here. You get this feature extending way downstream. That's called the anvil, the overhanging anvil cloud of the system. You'll note that in the schematic, they've also drawn most of the precipitation associated with the system on this same side, on the front side of the system. And it's the same basic idea. As the air feeds into the updraft and starts to produce rain and hail, that rain and hail gets pushed by the winds over here to the front side of the system. So most of the rain ends up actually falling here on the front flank of the system. Now, as you'd probably expect, tornadoes tend to form associated with this rotating updraft, typically. They'll be located right in this environment of the rotating updraft. That's not always the case. You sometimes can have tornadoes forming along the gust fronts as well. Sometimes you'll get little tornadoes along the rear flank gust front, for instance. But those are usually much weaker tornadoes and not very long-lived. The really strong tornadoes are mostly going to be associated with the rotating updraft. So that being the case, that raises the question, why is it that this updraft is rotating in the first place? Why does the updraft associated with the supercell rotate? Well, it turns out that the answer is that the rotation of the supercell is the rotation of the updraft of the supercell is ultimately going to stem from the wind shear in the environment. So the rotation of the supercell updraft ultimately stems from the wind shear in the environment. Remember, wind shear was the change in the winds between the ground and upper levels. And so it's going to be that change in the winds that's actually going to end up producing the rotation of the supercell. Now, keep in mind that supercells tend to form in high shear environments, right? So that's environments that have a lot of shear are the ones that are going to produce these rotating updrafts. And basically the way this works looks something like the following, like this schematic here. So over here on the left-hand side, we've got a schematic showing an environment in which the winds are blowing from the south. We've got southerly winds down near the ground, and then higher aloft here we've got northerly winds. So that's our environmental wind shear. That's our shear in the environment, that change in the winds with height. And you can imagine if you had your hands, and in between your two hands, you stuck a pencil. And then you moved your hands in the direction shown by these arrows here. That is, you move your lower hand in the direction of the orange arrows, and then move your upper hand in the direction of the blue. So maybe your lower hand goes away from your body, and your upper hand comes towards your body. That's representing the shear associated with the winds. And so what's going to happen to that pencil that's stuck between your two hands? Well, as you move them like that, the pencil's going to roll. And that's just indicating that this shear associated with the environment is sort of in a sense, it's a form of rotation, right? It causes that pencil to roll that's stuck in between your hands. So it's actually sort of a source of rotation. And what happens then is that as you take that rotation, and when it gets fed, when that shear gets pulled into the updraft of the storm, so that shear is a source of rotation, and when that shear gets pulled into the updraft, it ends up spinning about a vertical axis. Right, initially down here on the left-hand side, it was spinning about a horizontal axis. But when you took that thing and fed it into the updraft of the system, it tilted the whole thing upwards. And that ended up causing it to rotate about a vertical axis. It's kind of like taking that pencil that you're rolling between your hands, and then you rotate your hands, and the pencil ends up spinning about a vertical axis instead of a horizontal axis. That's more or less what's going on here to produce the rotation of the updraft. So the end result of that is an updraft that's rotating. It's called the mesocyclone, has a name. And that rotating updraft is an environment that's favorable for the production of tornadoes, in particular stronger tornadoes. That said, I should note that really this isn't an explanation in itself for tornadoes. This is really just explaining why the updraft rotates, which in turn is an environment favorable for tornadoes. But it doesn't actually produce tornadoes on its own. And in particular, most supercells don't produce tornadoes. The numbers are something like 20 to 25% of supercells end up producing tornadoes. So obviously you need something else in addition to this rotating updraft. And the processes that actually cause the tornado to form in this updraft are kind of complicated, and they're just actually sort of being teased out right now. People have known parts of it for a while, but the details are sort of being teased out at the moment. There were a couple big field programs recently, and from those field programs, they're starting to get a better idea of how this works. But I would say probably at the moment it's not 100% understood how you go from that rotating updraft to actually having a tornado. Okie doke. Here's an example showing what the rotating updraft can look like. It can be rather dramatic. So this is called a wall cloud, and it represents the outer edge of the spinning updraft. So the updraft's being fed into the storm more or less from the direction we're looking. And then as it gets pulled up and starts to rotate, eventually you start to get a cloud to form. And that cloud marking the outer edge of the updraft is called a wall cloud. And typically these guys will be spinning in time. You can watch it. You can sit there and watch it spin in time. Here's another example. I think I showed this one before. So this is the updraft being fed into the storm. You've got your wall cloud spinning here. And you can see that this one produced a tornado, whereas the one before didn't, but this one did. And then one more rather dramatic example. This one's from the textbook. So this is, again, the updraft into the system. You can kind of see the striations in the cloud indicating the, being associated with the rotation of the air as it feeds into the cloud here. That said, I have to imagine that this image was probably photoshopped a bit. I can't believe that it was captured quite this dramatically. But nonetheless, this is apparently a real system and produced a tornado. So let's talk a little bit about the environments that often tend to produce these supercells and by association tornadoes. And we kind of saw this already in the last screencast when we talked about that tornado outbreak case. We were listing the ingredients needed for a storm, and we looked at a particular outbreak case. So we've sort of seen this already, but just to review. So the kinds of conditions that are particularly favorable for tornado outbreaks and supercells are conditions where you've got a cyclone propagating here across, it's typically in the spring, propagating here across the southern part of the U.S. And out ahead of the cyclone, associated with the rotation around the low, you'll be pulling warm, humid air off of the Gulf. And then you've got your cold front, and you've got your jet stream aloft associated with the cyclone, because the cyclone's forming on the front side of the trough, remember. And so you've got all these pieces coming together, and this is a favorable environment for tornadoes to form. Maybe let's go through and list the ingredients here again. The ingredients that we need to get storms kicked off and to get severe storms in general. So the first ingredient was a supply of warm, humid air so that you can feed it into the cloud. And in this case, obviously, the warm, humid air is coming from flow off of the Gulf down here at low levels. Second ingredient that we needed was conditional instability in the environment. It's a little bit hard to see that directly from this figure, but the basic idea is that it's conditionally unstable because you've got warmer air down near the ground sitting below relatively colder air aloft. They've kind of got it listed here on the figure. They've got warm air being pulled off of the Gulf, and that's sitting below relatively cold air here aloft. You remember conditional instability is a state where the air in the updraft stays warmer than the environment. And that's more likely to happen if you've got warm air to start with, and then the air in the environment aloft is cold. If that's the case, then the air that's rising is more likely to be warmer than the environment and will keep going. So that's the kind of thing that will tend to produce conditional instability, warm air below, colder air aloft. Third ingredient that we needed was a lifting mechanism, a trigger, to get the whole thing started. In this case, there's two. You've got your cold front. As it propagates through, it kicks the air up in front of it upwards, and that can kick off storms. And the second thing that you have is your divergence at upper levels associated with the trough. So again, keeping in mind that this system is forming on the front side of the trough typically, because that's where the divergence is, which reduces the surface pressure. So over here on the front side of the trough, but the front side of the trough is also where it's where there's divergence. And when you have divergence at upper levels, that tends to draw upwards air from below to replace the air that's being diverged aloft. So that divergence at upper levels is then also a source of lifting. It tends to draw air upwards to replace it here on the front side of the trough. So there's two potential triggers, the cold front and then the front side of the trough, and they both play a role. And then the fourth thing that we need, these are what the ingredients that we need for storms in general. And the fourth was an ingredient that we needed for severe storms, and in particular for supercells, and that's a lot of shear in your background winds. We need shear in our environmental winds. And that shear in this kind of configuration is going to be provided by having the jet stream at upper levels. Because the jet stream is very strong wind, and it's going to be, if you're associated with the trough, it's either going to be westerly or sort of southwesterly, depending on which part of the trough you're looking at. And so you got really strong winds aloft. You've got weaker winds down at the ground associated with the flow off of the Gulf. So that gives you a really strong change in the winds with height. It gives you a lot of shear, and that's what you need to produce supercells. So this kind of configuration then sort of provides all the ingredients that you need for supercells. This is actually why the U.S. produces so many more tornadoes than other countries. It's because we have these conditions that that set up favorably in the spring for tornadoes. This is that same case that I showed before, showing all the same ingredients, flow off of the Gulf, cold front, divergence at upper levels, the jet stream, so forth and so on. So let's quickly talk about tornado intensity. Now, tornadoes aren't actually measured directly in terms of wind speeds. There's nobody, for the most part, for most tornadoes, there's nobody out there trying to take wind measurements associated with the tornado. So typically you have to infer how strong the winds were in the tornado by looking at the damage it caused. That's typically how it works. You kind of go through and look at the damage and try to infer how strong that tornado was. So what that means is that the scale of tornado intensity is actually a damage scale. It's a tornado damage scale. And it's called the Fujita scale. It was devised by a guy named Ted Fujita, and he went out and looked at a bunch of cases. I think he did this in the 70s, if I remember right. And looking at a bunch of tornadoes, he tried to, knowing what he knew about winds and damage to structures, he tried to infer how strong those tornadoes were going to be. And so he ended up coming up with this scale. And it was ended up being revised a little bit in 2006 to be a little bit more accurately representative of the winds. And so the scale that they use now is called the Enhanced Fujita scale. Why use the Fujita scale when you can use the Enhanced Fujita scale? But it supposedly a little bit more accurately represents the strength of the winds in the tornado. So how's it go? Well, so it's got 6 categories, starting from EF, standing for Enhanced Fujita, EF0 through EF5, 6 categories. You can see the winds associated with these guys here, written in green, starting at about 60 miles per hour, and then the next one starts at about 80 miles per hour, 85, 110 miles per hour, 140 roughly miles per hour, 170, and then greater than 200 miles per hour. And then the kind of damage that's associated with them. Well, the EF0s are the weaker tornadoes, and the damage that they produce is typically pretty light to well-built structures, things like ripping off roof shingles and stuff like that, as you can see in this photo. You step up to the EF1s, and the EF1s will start to produce some damage to things like windows and doors, and they'll also do more significant damage to the roof, things like that. Step up to EF2s. EF2s can do quite significant damage to buildings, tearing off roofs and things like that. At EF2, I think that's where you actually can start to lift a car a little bit associated with the tornado. EF3s, Obviously, as shown by this photo, you're starting to do significant damage to the structure with an EF3. This is the kind of thing that can start to blow a car, move it from one place to another, lift the car up and move it from one place to another. You get to the EF4, and you're starting to talk about pretty much complete destruction of even well-built homes with EF4s. EF4s are very dangerous, obviously. And then EF5s, same kind of thing, complete destruction of the structure. And the distinction between the EF4 and the EF5 typically is that the EF5 will completely destroy the structure and rip everything away. So there's nothing left except for the foundations. You go out and look at EF5 storms, and basically you see a bunch of home foundations. That's the only thing left in EF5. Now, it's worth going through and noting how frequent these kinds of storms are. And as you probably would expect, most of the tornadoes, or at least the majority, end up being EF0s, the weaker tornadoes. A little more than half of the tornadoes that form are EF0s. And then about another third or so are EF1s. So if you put those two together, you're talking 86, 87% of the tornadoes are going to be EF0s or EF1s. The more stronger tornadoes, the EF2s, which can start to do significant damage to the buildings, that's about 10%, 11% of tornadoes. And then the really strong ones that cause destruction of buildings, the EF3s and above, you're talking about 3% that are EF3s, about 1% are EF4s, and then a very small fraction, about 0.1%, are EF5s. So the really significant tornadoes that do a lot of damage add up to about 4 to 5% of the total. I'll note that the EF5s in particular, if you sort of multiply this out, in the U.S. on average there's about 1,000 tornadoes per year, and so 0.1% ends up being about 1 EF5 per year produced in the U.S. Now it's not quite so it's not as regular as that would suggest. There are many years where there are no EF5s. For instance, I think it was about 8 years or so in a row from the 1999 into the early 2000s, there were no EF5s produced at all. And then in 2011, we had a bunch of tornado outbreaks, and there were 6 in 1 year, 6 EF5 storms. But on average, it's about 1 a year in the U.S. Now, I should note that these numbers are numbers for the U.S. If you go to other parts of the world, they're much more heavily skewed towards the lower end. The U.S. produces a lot more lot more powerful tornadoes than other parts of the world. So other parts of the world are more likely to have the weaker tornadoes. I guess I should say that there are other parts of the world that do produce significant tornadoes and supercells. There's I forget exactly what they call it, the tornado corridor. I used to remember that exactly. But in South America, there's a region sort of leading through Argentina in particular, where they produce a lot of supercell tornadoes. But the U.S. produces the most by far. So speaking of that, where are the tornadoes most likely? So this is showing frequency of tornado occurrence, average number of tornadoes per year by state. And the top number here for each state is going to be the total number of tornadoes. I believe the bottom number is the number of tornadoes per unit area of the state. So it's been normalized by the size of the state. Should double check that. It's either per unit population or per unit area, but I'm pretty sure it's per unit area. And so by this measure, the bulk of the tornadoes are forming sort of right in this region in here. This is your tornado alley. So you've got, 8.2 here in Oklahoma. That's the highest, 8.2 per unit area, whatever the unit area was. And then 4.7 for Arkansas, 5.7 for Alabama, Louisiana 5.6, 5.2 for Texas. So this is where the bulk of the tornadoes is going to be, right in here. Nebraska as well, 5.8. So right in this region in here, it's going to be where the bulk of your tornadoes are forming. Kansas as well. And again, the reason for that is just the structure that we saw before, stepping back to that, where you've got these cyclones propagating through, interacting with the warm air coming off of the Gulf, and that's a favorable condition for tornadoes. Notice that you get quite a few tornadoes here in Florida as well. What's the number on that? 9.4. It's actually the highest of the bunch. But the tornadoes that produced in Florida are typically not going to be supercell tornadoes. You don't get very many supercell tornadoes in Florida. Most of those are going to be much weaker tornadoes associated with multicell storms. Number of tornadoes by month. The bulk of the tornadoes is going to occur here in May and June, sort of the late spring, early summer. That's when it's warm enough that you're getting significant warm, humid air coming off of the Gulf, and you still have cyclones propagating through in that time of the year to set all of this off. As you go into later summer, they start to tail off the number of tornadoes, and that's mainly because the cyclones associated with the sort of favorable conditions for these tornadoes, all of that's moving northward. If you remember when we talked about the jet stream migrates north and south with the seasons. And so as the summer moves on, the jet stream migrates further and further and further north. The cyclones associated with it move further and further and further north. And so you're less likely to have the conditions set up for tornadoes in the U.S. In fact, you're starting to get into August, maybe early September, you're probably more likely to see tornadoes up in Canada at that point than you are in the U.S. because all of that has moved northward. Time of day, tornadoes are going to be most likely here in the late afternoon. That's when the storms have, sort of warmed up, the ground's warmed up enough to start kicking off storms. And so by late afternoon, early evening, so 5, 6, 7 p.m., that's when you're going to have a lot of these storms having been kicked off, and that's when you're going to have your tornadoes. You do have some tornadoes that form overnight, though, sort of extending long into the overnight hours. Most of those are going to be associated with big systems, so big collections of storms with embedded supercells in some cases that propagate through. Some of those things can be very long-lived. They can live 12 hours, say, overnight, and some of them will produce tornadoes. Okay, finally, speaking of which, big collections of storms. So in addition to our 3 basic storm types, which were our single cell, our multicell, and our supercell, you can also have big collections of these things. So, a bunch of multicell storms all forming sort of in the same general area, if you like. And these collections of storms forming in the same general area are called mesoscale convective systems. There's 2 sort of classic types of mesoscale convective systems, which are defined based on the organization of these storms. So the first is the squall line. The squall line. And the squall line is just a collection of multicell, or in some cases supercell, but less often. So a collection of multicell or less often supercell storms that organize themselves into a line. That's basically what a squall line is. So you've got a bunch of these storms all forming at the same time, and they organize themselves in sort of a linear fashion, as indicated in this figure here. And as you can see in the figure, these squall lines can be really long, right? They can extend across a number of states all at once. But within the squall line, you've got a bunch of individual storms that are forming sort of, have their own identity, if you like. But they're all forming in this same general region, organized into a line. And typically, this is going to happen associated with your cold fronts. As your cold front propagates through, it's kicking off a bunch of storms, and they're all going to be kicked off sort of along this line, along the cold front, and so you end up with a squall line. Once it forms like that along the cold front, it has its own sort of life, and so it can actually propagate out in front of the cold front a significant distance. But typically that's what's going on. There's some boundary along which these things are forming, and that's why they're arranged in a line. And then finally, you can also have systems where the storms just all sort of form in the same region but don't have any specific shape associated with them. And these guys are called mesoscale convective complexes. Mesoscale convective complexes, which is a lot of syllables, so we usually call those MCCs, mesoscale convective complexes. And the mesoscale convective complex is just a collection of multicell storms that are all just forming in some region without any specific organization to them. They usually just end up being sort of a blob of storms on a radar image. This is an example here, and you can see, again, these things can sometimes be quite big. This is a really big case, but, this covers like basically the whole state of Oklahoma and parts of Kansas, and most of Kansas, I guess. So it's a really big complex of storms all forming in the same environment. And these guys can be very long-lived. These guys can live for, in some form for a couple of days because they have sort of their own self-reinforcing organization. I guess the last thing I'll point out is that when these collections of storms form, the squall line is more likely to form in an environment that has a fair amount of shear associated with it, which is often the case with cold fronts because the cold front is associated with a cyclone, which has the jet aloft. Whereas the mesoscale convective complex typically just forms an environment without much shear, and all these things just sort of form in a random way. Okay, so we're going to leave it there.